talk about scientific notation. Scientific notation, it's called that because they use it in science, because in science specifically, physics, astronomy, chemistry, and a number of other sciences, you can sometimes get very big numbers and very small numbers. And if you have something like 0.0032, you want to be able to write it down compactly, otherwise there's a danger of losing track of all the zeros. And if you're wrong, and if you miss that, then you're off by a factor of 10. In other words, really wrong. So here's what we do. You write the number in this form, n times 10 to the power p. This number n is at least 1 and strictly less than 10. 10 to the power p, p is a whole number, the magnitude of that number. So for example, 3.2 times 10 to the negative third, this negative power means it's really small, 1,000. What we do is we take this decimal point and we move it to the left 1, 2, 3 spots. So 1, 2, 3 spots. Or another way to write it is you put a 0 just to the right of the decimal and then write 3 zeros. 0.0032. 3.2 times 10 to the third, 10 to a positive number is going to be a big number, in this case, thousands. So we're going to move this decimal point 3 places to the right. 1, 1, 2, 3. 3,200. Here we have 137,000. Okay, so the n part, I think it's called the mantissa. It's always going to be between 1 and 10, so I write the decimal point just to the right of the leading figure, 1.37. So we move the decimal point how far? 1, 2, 3, 4, 5 places. So it's 1.37 times 10 to the fifth. Here's 0.00137. Again, we're going to put the decimal point just to the right of the leading figure, 1.37. And we have to move the decimal point 1, 2, 3 places to the right. So it's 10 to the negative third. So 1.37 times 10 to the negative third. I interpolated this page after writing it because I realized, so that's why it's page 1.5. If you have orders of magnitude, well, they have special names. For example, a number between 10 and 99, that's going to be something times 10 to the first. So these are in the tens. 100 and 999, those are in the hundreds, 10 to the second. 1,000 and 9,999, that's in the thousands, 10 to the third. Now, there's fourth and fifth powers. Those have magnitude names, but I haven't heard them that often, and I think they're useful, so I'd like to introduce them, because they do have some precedent. If it's something between 10,000 and 99,999, that's the hundreds of hundreds, 10 to the fourth power. That has a name. It's called a myriad. And if it's 100,000 to 999,999, that's in the hundreds of thousands, 10 to the fifth. That also has a name, multitude. Okay, now if it's 10 to the sixth power, 1 million between 9.99999 million, that's in the millions. If it's the ninth power, 1,000, 1,000, 1,000, and 9.99999,000, that's billions, thousands of millions. And 1 followed by 12 zeros up to 9, followed by 12 nines, that's 10 to the 12th power, called trillions. Oh man, I used to remember when talking politics, billions is about as big a number you'd get. There was a senator who said, oh, a billion here, a billion there. Pretty soon that adds up to real money. I think these are really used. I haven't seen them used that often, but they do exist in the literature. And I recommend them. I mean, for example, oh my gosh, I don't know how many remember the first Gulf War? Any of you? Oh my God, time flies. Well, all I can say about it is that when George, I think W. Bush, wanted to get into war, and he did, of course, but people were objecting. So I remember vividly that I and my wife got up and we put Hannah got Hannah in the crib, and we took her down to Market Street. And I think every so often people should just take over the streets, just walk down the center lane, just to say, hey, this is our city. It's not the Cars city. Just for that only. Anyhow, she was Sherry wanted to say, do I have to get up and miss history? I said. So we went there. So all right, and it was a huge march going from the Ferry Building all the way to City Hall, just jam-packed, the whole thing. And it was an enormous thing. It was hundreds of thousands of people, so multitudes. But I gotta tell you, the very next day, the San Francisco Chronicle put that on page A15 and said thousands march. Excuse me? Thousands? That's 1/100th of multitudes. I think the phrase multitudes march just has alliterative quality to it, which they missed out on. And shortly afterwards, I canceled my subscription to the Chronicle. Anyhow, so these are useful names for orders of magnitude. All right, we use scientific notation for writing very small or very large numbers. We look at all those zeros and look at all those zeros. I mean, you've heard of the phrase astronomically big, right? Well, because astronomy, you have these enormous numbers and sometimes incredibly tiny numbers. So here, this number, what is it? Well, it's 2.03 times, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. 2.03 times 10 to the negative 9. As you can see, there's a lot more compact way of writing it down, and there's less chance of losing a zero, which of course would be a very bad thing. Here's this horrendous number. So it's 5.016 times 10 to the power of what? 3, 6, 9, 12, 15, 16. 5.016 times 10 to the 16th. Now, sometimes you get a number which is not quite in scientific notation. 23.65 times 10 to the 6th. The problem is that this 23.65 is not between 1 and 10. So what we do is we adjust it. We write 23.65 as 2.365 times 10 to the 1st. That times the 10 to the 6th, we add these exponents and get 2.365 times 10 to the 7th. Or here this, 0.0317 times 10 to the negative 2. Again, this is not between 1 and 10, so we adjust it. So we write 0.0317 as 3.17 times 10 to the negative 2. That times 10 to the negative 2, you add the exponents and get 3.17 times 10 to the negative 4. All right. Now, part of the purpose of scientific notation is not only for denoting numbers, but also for operating with them, multiplying and dividing them. It makes it in some ways somewhat easier. For example, 1.3 times 10 to the 4th times 7.8 times 10 to the 5th. What is it? The point being is that we multiply these parts, and then we multiply the magnitudes. Well, it's easy to multiply magnitudes. 10 to the 4th times 10 to the 5th is 10 to the 4 plus 5. Now this 1.3 times 7.8 is 10.14. That times 10 to the 9th. However, this is not in proper scientific notation because this is bigger than 10. So I rewrite this 10.14 in scientific notation. 1.014 times 10 to the 1st. That times 10 to the 9th, you add the exponents. I get 1.014 times 10 to the power 10. Or here, 2.686 times 10 to the 10th over 7.9 times 10 to the negative 7. Okay, we divide these parts, 2.686 over 7.9, and then you multiply by the ratio. Well, okay, here we have a ratio of powers of 10, so we subtract 10 minus negative 7. Okay, 10 minus negative 7 is 17, so you get 10 to the 17th. This, after a brief visit to the calculator, is 0.34. But again, this is not in proper scientific notation. We need to adjust this. 0.34 is 3.4 times 10 to the negative 1. That times 10 to the 17th, you add the exponents, and you get 3.4 times 10 to the 16th. I would do some examples. 9.1 times 10 to the negative fifth times 5.5 times 10 to the 12th. Oh, you would multiply the 9.1 and the 5.5 and get 50.05. You add the exponents here. Negative 5 plus 12 is 7. However, this is not in right form, so we rewrite 50.05 as 5.005 times 10 to the first. That times 10 to the seventh, we add the exponents, and we get 5.005 times 10 to the power 8. There's the answer. You have 2.193 times 10 to the 32nd over 4.3 times 10 to the 20th. Okay, we divide I guess we'll call them mantises. 2.193 over 4.3. We subtract the powers, 32 minus 20. This part here comes to 0.51. This part here comes to 10 to the 12th. Again, this is not in proper scientific notation. So we rewrite 0.51 as 5.1 times 10 to the negative 1. That times 10 to the 12th. You add them up and you get 11th power. So 5.1 times 10 to the 11th. Okay, this is a mess. And they asked to write it in scientific and in standard notation. 0.0000000039 times 0.00095 over 0.0195 times 4,000. Oh boy. Okay, well, if you count zeros here and here and here, you get this is 3.9 times 10 to the negative 9. This is 9.5 times 10 to the negative fourth. This is 1.95 times 10 to the negative 2. All right, and then this is 4 times 10 to the third. All right, so you multiply all these mantises out. 3.9 times 9.5 over 1.95 times 4. In the numerator, 10 to the 9th times 10 to the negative 4th, we add those and get 10 to the negative 13. In the denominator, we add negative 2 and 3. 10 to the negative 2 plus 3 is 10 to the first. Okay, this part, after consultation with the calculator, you get 4.75 times this ratio. Here we subtract the exponents, negative 13 minus 1, that's negative 14. So you get 4.75 times 10 to the negative 14. That's in scientific notation. To write it in standard notation, I write the 475 and then write 14 zeros in front, 0.00000. A light speed is about 300 million meters per second. A light year is how far light travels in a year. How many meters is that? Okay, first we have to figure out how long a year is in seconds. You take a year, then you multiply it by this. It's called a unit ratio, a unit conversion ratio. The idea being that these two are equal. 365.25 days is the same as 1 year. So the ratio is 1, so you can multiply a year by that. The idea being that this way the years cancel. 24 hours per day, that's another unit conversion ratio. 60 minutes per hour is another unit conversion. 60 seconds per minute. So, okay, years cancel, days cancel, hours cancel, minutes cancel. We're left with units of seconds. 1 times 365.25 times 24 times 60 times 60 is about 31 million seconds. A while back, I went to the trouble of figuring this out just because I was curious. And I got to tell you, it gave me this terrible feeling of mortality. Because I asked myself, how long is a billion seconds? Turns out to be about 30 years. And again, 30 years, it's like only a billion seconds. Oh dear. I calculated it, and it turns out that my second billionth second will come in the middle of March next year. And I intend to do a Zoom party with some of my friends. So again, only 2 billion seconds, and it's most of a lifetime. Oh my goodness. Anyhow, so a year is this many seconds. So a light year is that speed, 300 million meters per second, times 31 million seconds. Seconds cancel, 300 million times 3,1557600. Blah, blah, blah. Okay, we turn this into 3 times 10 to the 8th. We turn this into 3.15576 times 10 to the 7th. And multiply it out, 9.46728 times 10 to the 15th meters. Let's see, so 9.46 quintillion meters. And that doesn't even get us as far as 1/4 of the way to Proxima Centauri, which is the nearest, which has the nearest extrasolar planet. It's a big, big universe. Well, I believe that's it for this section. Stop recording.